All right, the last section that we're going to talk about in Chapter 7 goes right along with a lot of the stuff that we've been doing throughout the course of the entire year. And what we're going to do is we're going to talk mostly about how you transform logarithmic equations and also exponential equations. I guess I should say functions, not necessarily equations. Now, the rules for how we do this really aren't going to vary much at all in comparison to what we've done before with linear functions and quadratic functions and even just polynomial functions in general, as far as translating them left and right and also up and down, applying compressions and stretches, and also reflecting things across different axes. Okay, so like I already said, you can perform the same transformations on exponential functions and even logarithmic functions that you did on polynomials, quadratics, and linear functions. All right, now we should all be pretty familiar with what this looks like. Okay, how the different transformations and translations work in comparison to each function. Okay, now the only thing that is a little bit different is going to be when we talk in terms of parent functions. Okay, with linear functions, it didn't really matter what we did with them. Your parent function for linear functions was always just y equals x or f of x equals x. With quadratics, your parent function was always just x squared. Okay, and there was a similar way that we approached polynomials in terms of, if it was x squared, x to the third, x to the fourth, so on and so forth. Okay, parent functions for exponential functions are a little bit different, okay, because they can be a little more, I guess you say a little more generalized, okay, as far as you might not necessarily have something as simple as x squared or as simple as x, but it'll make sense when we get into using it. So just make sure you remember how all these rules work, how applying them to each function results in the indicated transformation. Okay, so it's something that you want to write down if you don't still have it to reference from when we talked about it earlier. Okay, and this is just a hint as far as the h in those original equations just represents horizontal and stuff like that. Okay, now again, I'm not going to worry so much about you having to graph these longhand. Just remember, like anything else, if you really want to graph a particular function, you can just pick random values for x, fill them in, get a corresponding y, and then you have points that you can put on your graph. Like we talked about earlier with exponential functions and even logarithmic functions, most times it's a lot easier if you just use some type of graphing calculator or a graphing program that can in turn give you the table if you need the table. It makes things a lot easier, and that's just how I'm going to kind of approach this. All right, so what I have here is, it's one of those things where you could make a table to figure out how to graph g of x. I'm just going to give that to you, and when you get something up here that looks like this, okay, the blue function would represent your f of x, the g function would represent your g of x. Okay, as far as graphing those, and that would all be something that you could do on a graphing calculator if you wanted to, so you can see both of them work. What I'm more concerned about here is understanding, all right, that first of all, this is my parent function down here, my f of x, but understanding how f of x differs from what's written right there. Okay, now the first thing to understand here with exponential functions is to determine what the parent function is, you just want to look at the part of your function that has the variable in it, or where the variable is an exponent. Okay, now this says 2 to the negative x, and we should all be pretty familiar with the fact that the plus 1 behind it just means that we're taking the parent function and we're shifting it up 1 unit. Okay, but if you look at the part that has the variable in it, if you remove all types of transformations from that particular part, you figure out what your parent function is. So if I get rid of that negative that's up there, that's how I understand that what I have written down here is my parent function. Okay, so let's think about this for a second. Essentially, what we're doing is we have that plus 1 behind up here. Okay, well, plus 1 means that I'm taking my parent function down here and I'm shifting it up 1 unit. Okay, so that's one translation. Okay, a vertical translation by 1. Okay, the other thing we have to look at is in here, I have a negative x when compared to my parent function where it says positive x. So what that means is I'm taking my parent function and I have taken and made the x negative. Okay, so what that means is it's some type of reflection. Okay, and when you take something and you make the x and only the x or the input value is negative, that means that you have some type of reflection, and in this case it's a reflection across the y-axis. Alright, so my two transformations, or translations in this case, that are taking place are a reflection across the y-axis, which is represented by this, or by taking your x and essentially making it negative like we see over here on the right. Okay, and then also the plus 1 behind it. If we take our parent function down here and we add 1 behind it, that means we're taking it and we're shifting it up, or translating it up 1 unit. So those are my two transformations in that particular case. Alright, here's another example. Again, if you wanted to graph it, you could go ahead and fill out a table and do all that stuff. I'm not going to worry about that a whole ton. Okay, again, we're trying to figure out how do we take our parent function, which should be a little bit easier to identify in this case because I just have 2 to the x right there. Okay, 2 to the x, and how do I get to what I have up there? Now what you'll notice this time around is that minus 2 is up with the x in the exponent. Okay, so that doesn't mean that I just added or subtracted it to the whole function. That means I actually subtracted it with the x value. So I took my original f of x parent function and I took and filled in x minus 2 wherever there was an x, meaning I changed the input values, okay, by subtracting 2 from them. So what that does, you remember the whole x minus h thing in parentheses, means that I take my function, my original parent function, which would be in blue down here, okay, on the graph, and I have shifted it 2 units to the right. Alright, so this one's a little bit simpler. Alright, the minus 2 in with the x just indicates that I'm taking my parent function, which would be this down here, and I am shifting it 2 units to the right. So everything else about that function is exactly the same, okay, just a little bit different in terms of where it is located on the graph. Okay, here's another example. Alright, this one's just a little bit different. It says find the y-intercept and the asymptote and all that stuff. So I'm going to go ahead and I'm just going to throw the graph up here again so we can take a look at it. Now, looking at this one again, okay, the parent function is just going to be the part that is raised to the exponent. Okay, so in this case, my parent function is just going to be 1.5 to the x. Okay, anything else that's being applied to that is some type of translation or transformation. Okay, so the next thing it says find your y-intercept. Well, if I'm looking at what I have down here, okay, to find your y-intercept, it's a little bit different. You know, with linear equations or functions and quadratic, it was always just that last constant that was there if things were written in standard form or in slope-intercept form. With something here, the easiest way to find your y-intercept is just fill 0 in for x, alright, and see what you have left when you're done. Because remember, if you have anything that is on the y-axis, its x value is going to be 0. So if you fill 0 into your function, okay, if I fill 0 in right here, alright, that means whatever's left is going to be my y-intercept. Well, if I put 0 in for x, this whole 1.5 part ends up being 1, okay, because 1.5 to the 0 is 1. 1 times 2/3 gives me 2/3. So my y-intercept is the 0.0 2/3. Or if you just wanted to say, you know, 2/3 is your y-intercept, that would work too. If you're thinking in terms of your parent function here, which we have up here, your y-intercept for your parent function is just going to be 1, okay, which you can see in blue over on the right. Because again, if you fill 0 in for x, anything to the 0 power is 1. So you fill in 0, you get 1. So we can see that over there. Alright, now describe how the graph is transformed. Alright, now the other thing to keep in mind, I guess before we worry about transforming, is it does say find the asymptote. Now you can see the green dotted line there on the right represents the asymptote. And like I told you before, and this was back a little bit when we first introduced these functions, but as long as there's no vertical or horizontal, I guess I should mostly say vertical, as long as there's no vertical translation, we're not shifting anything up and down, your asymptote is going to be the line y equals 0, like it is right here, or it's going to be the x-axis. Now once you start shifting things up and down, that asymptote is going to change a little bit. Likewise, if you start reflecting things and shifting things, it could possibly change. But in this case, there's nothing written behind here as far as me moving anything up and down, and I don't have any negatives listed out front representing reflections or anything, so I know that I'm not going to have any type of asymptote shift. Okay, so your asymptote is going to be y equals 0. Remember, asymptote, that dotted line, is just the imaginary line that our graphs approach. Okay, and we'd be talking about as we move out here to the left. Okay, because we have growth going to the right. As we move to the left, it's the imaginary line that my graphs are going to get really, really close to, but they're never actually going to touch. Okay, now the other aspect of this is it says describe the transformation. Well, basically what I have here is I have a 2/3 being multiplied out front. So in other words, if f of x was my parent function, to get to what I have here, I took 2/3 times that f of x function, and that's how I got to what is written up here. Okay, so if I take 2/3 times an entire function, meaning I'm taking 2/3 times all the output values, or basically all the y's. All right, I have taken and I have compressed things from a vertical standpoint, or I multiplied by the y's or the outputs, and because it's a fraction between 0 and 1, I have compressed things vertically, and that's why you'll notice the graphs on the right there. Okay, your blue line would be your parent function, the 1.5 raised to the x. The red line there would represent the g of x, or the transform function. You'll notice how it's a little bit lower than the blue one would happen to be. Alright, here's another example, and I'll go ahead and graph what I have up here as far as what the graphs look like. Alright, now the only thing different about this is instead of having a number as the base of our exponent, we have e. Now remember, e is still a number. Okay, it's like 2.718, something along those lines right there. Okay, but we represent it as a letter, but it's still a number, so you just need to remember that. Alright, so in this case here, your parent function, again, parent function is basically the base of whatever the exponential part is. So my parent function is just going to be e to the x here. Okay, so now we need to think about, okay, your asymptotes. Alright, you don't have anything back here as far as moving anything vertically. Okay, you do have a negative in here, which means that there's some type of reflection, but based on the graphs, there's no reflection going across the x-axis. It looks like it's just y. Alright, so your asymptote is still going to be y equals 0, and you can see that from the green line down there. Okay, now transformations. Okay, I have a negative in with the x, so that means I'm taking my function, and so I should probably draw an arrow, and I'm putting a negative in with the x, and then it also looks like I have a +1 in there. Okay, a +1 that happens to be in there in parentheses. Okay, with the x, so I'd be putting a +1 in with the x. Alright, so I'm going to just show this one first. This is going to represent the across the y-axis thing, and then it shows a +1. Now this is where things can get a little bit confusing. Alright, because if you look at your graph, okay, it looks like we shifted. You can see the reflection from the blue to the red line, okay, across the y-axis, which would be represented by this here, by changing your x values. Positive x becomes a negative x, so on and so forth. Alright, it's the +1 part there that can be a little bit misleading. Alright, because technically it would be a -1. You'd be putting a -1 in there, but the negative that goes with the x would change it to a plus. So really what's going on here is you're really putting in a, I should probably write this the right way, it's an x minus 1. Alright, so you're actually shifting or translating things 1 unit to the right. Alright, but because this negative up here also goes in with the x, what it does is it takes and it almost changes it like that. So that's how you arrive with what's going on up there. Alright, so if you change all the x's to negative, understand that it's going to affect that 1. So really what this is representing is a reflection across the y-axis, but then it represents a shift or a translation 1 unit to the right, not 1 unit to the left. And that's where this in here can be a little bit confusing. Normally if we see x plus something or plus something at the x, it represents something shifted to the left. But in this case, this negative that has gone in with the x to provide a reflection indicates that that would be the reason that that sign got switched to a plus. So it still represents a shift of 1 unit to the right. All right, so just something to keep in mind there if you see a negative with the x and also a number behind with the x. All right, now logs, pretty much going to work the same way. The same rules are going to apply to most of this stuff. Okay, and this is basically just a repeat of the chart that you saw earlier. The only difference being the examples on the right side represent log functions as opposed to exponential functions. All right, now one thing to keep in mind here is just that any transformation that was shown on the previous slide that dealt with logs also works for natural logs. Because remember, the natural log of x basically just means a log with a base of x, or the way I explained it the other day was just think about it this way. All right, if you have a natural log, the base is technically like an e there. Okay, so something to keep in mind as we think about this. All right, now again, I'm going to go ahead and graph what's going on here. Okay, because it's something that graphing these, you can always take values of x and fill them in and get corresponding y's to figure out points. But the easiest way with these, because they do tend to get a little bit complicated, is to just use a graphing calculator, a graphing device to do that. Okay. Now, as far as these are concerned, as long as there is no translation in with the x, or a translation as far as moving things left and right, your asymptote, okay, is going to be the y-axis, or x equals 0, as you can see with the dotted line that's there. Now, if you would start moving things around in with the x, that vertical asymptote is going to shift left and right. Okay, so something to keep in mind if you're asked to find asymptotes. Say our graph had been shifted 2 units to the right. Okay, well then my asymptote would have to be x equals 2. It would move over here a little bit more to be on that line. Okay, so just something to keep in mind if you start shifting things left and right. Your vertical asymptote, or that imaginary line that your graphs are going to approach but not touch, is not set in stone on the y-axis. It can shift left and right. All right, so something to keep in mind. But in this case, it is just x equals 0. Okay. Now, the next thing we want to keep in mind here or look at is what's being done here. It looks like we're subtracting 2 from the function, and we're taking the entire function times 5. Okay. So we're taking our parent function, which in this case our parent function is just log of x. Okay, we're taking our parent function, our f of x, and we are first taking and we are moving it down 2 units. So I'm taking the entire function and I'm subtracting 2, okay, which would represent your vertical translation by -2 units, or down 2 units. And then I'm taking the result of that, which we could still call f of x. If you wanted to call it something different, you could. But we're taking that times 5. All right, which represents a vertical stretch of 5 units. Okay, so vertical translation down 2 units, vertical stretch by a factor of 5. And that's why you'll notice, okay, most of these, if we look at it, their y values would decrease by 2, and then the y value would actually increase by a factor of 5. That's why the red line looks significantly different from the blue line over there on the graph. All right, here's another example, and this one's kind of similar to the last exponential one we did, where you'll notice there's a negative in here followed by a plus, or an addition of 2 in with the x. Okay, so we'll graph these again just so we can look at what's going on here. Okay, remember, blue is your original, or blue would be your parent function, which in this case is just the natural log of x. Okay, red represents what's going on after the translations. Okay, now we'll look at the graph here, and then we'll kind of come back. Now you notice your asymptote is a little bit different on this one. All right, and I'll explain why it's a little bit different here in a second. But let's think about this in terms of what we did before. You see a negative in with the x, so that means we took and we basically changed all our x values around. So that represents a reflection across the y-axis, the negative part. Now, the other thing to keep in mind is you do see what looks like a +2 up here, which would normally, you would think, oh, that means that I'm shifting my graph 2 units to the left. But again, because this negative is in here, originally it started out as x minus 2. Alright, but the negative in here takes and makes the x negative and changes the translation and makes it look like it's a plus. So in reality, it started out as an x minus 2. Okay, so if it began as an x minus 2, that actually represents a shift 2 units to the right. Alright, so we have a shift of 2 units to the right, and we also have a reflection across the y-axis. So those would be my transformations that are taking place here. Now, because this represents a shift of 2 to the right, you will notice how my asymptote has also shifted 2 to the right. Instead of being x equals 0 or being right on the y-axis, in this case my asymptote is x equals 2. Okay, or the vertical line that goes through 2 would represent the imaginary line that my newly translated graph, my h of x, is going to approach, but it's never ever going to touch. Alright, and really the only reason that would come into play would be to help you in terms of figuring out domain and range in particular cases here. Alright, this kind of gets into the stuff that should be a little bit easier for us now, the stuff that we kind of focused on when we were doing translations and transformations before. This is just taking an original function and showing what happens when something's reflected, translated, transformed, and coming up with a new function at the end. So if our parent function is 4 to the x, and it says it's reflected across both axes and then moved down 2 units. Okay, a reflection across both axes would mean we're taking and making the whole thing negative, which would flip it across the x, and we're also making it negative on the inside, which would flip it across the y, and then we are moving it down 2 units. So if I apply both of those to what's going on here, okay, basically what I would get is I'll call my new function g of x. Okay, so I would have negative 4 to the negative x minus 2. Okay, so just something to keep in mind there as you're looking what's going on. Alright, the negative out front here just represents the fact that we're going to flip it across the x-axis. The negative in here means that we're going to take it and we're going to flip it across the y-axis, and the minus 2 means we're shifting everything down 2 units. Alright, here's another example, and I'm going to go ahead and graph this here just because it'll help us take a look at what's really going on. Okay, so our parent function is a natural log of x. It's compressed horizontally by a factor of 1/2 and moved 3 units to the left. Alright, so if we start with our parent function and we say it's compressed horizontally by a factor of 1/2. Remember, if you're compressing something, that means you put 1 over whatever your factor is, okay, in with the x, alright, and then it's going to be moved 3 units to the left. So technically, I probably should have put a minus 3 in there afterwards. Okay, so 3 units left, sorry, plus 3, not minus 3. Okay, so let me rewrite that a little bit so you can just kind of see it a little bit better. I kind of crammed it all together there. Alright, so 1 over the factor that we are compressing by is anything horizontally. Okay, you have to put it in with the x. So 1 over that. So 1 divided by 1/2 is actually going to be 2. So it's going to be like 2x, and then I have a plus 3 written behind it. Okay, so more or less what's going on here is if I actually apply that to the function, I have the natural log of 2x plus 3 would be my new function. Okay, so stretching things by 2, then shifting 3 units to the left. Alright, and like I said, that's one of those things that we should be somewhat familiar with because that's a lot of what we did before. Now you also have a couple story problems that go with this. It's just one of those things where they're not super complicated. It's just one of those things where you just have to look at what's going on and figure out the different transformations that are taking place. Okay, so if I look at what's going on here, I have a function that represents the temperature in degrees Fahrenheit that milk must be kept at to last so many days. Alright, and describe how it's transformed from the parent function would just be the natural log of n in this case because we're using n as a variable. So if I look at what I have here, I have t of n and I'm going to just kind of move this part and shift it around just a little bit. So I'm going to say I have negative 16 natural log of n plus 75. Okay, just rearrange it so it's written a little bit easier in terms of what we're looking at. So what this looks like as far as how it differs from the parent function, as we were looking at a looks like a reflection across the x-axis, all right, which would be represented by this right here. Okay, we have a factor of 16 in front, so we would have a stretch, a vertical stretch by 16, and it looks like, so the vertical stretch by 16 would be represented by that. So again, reflection across the x-axis, stretch by 16, and then I also have this plus 75, which would represent a vertical translation of up 75 units. Okay, now it says use the model to predict how long milk will last if kept at 34 degrees Fahrenheit. All right, well, 34 would be my number that goes out there. I guess you don't really have to write the temperature sign with it, but I did. Okay, so it looks something like this. So what we're going to do is we're basically just going to solve for n. Okay, if we want to figure out the number of days that it can be kept at 34 degrees. All right, so I would subtract 75 from both sides. All right, so if you subtract 75 from 34, you get negative 41 would equal negative 16 natural log of n. All right, then we're going to divide by negative 16. So negative 41 divided by negative 16. Oops, probably need to make sure. The negative 41 divided by negative 16. You're going to get a decimal number here. All right, which story problem is probably okay to get a decimal here. So I'm going to write it over here. 2.56 approximately equals the natural log of n. Okay, now remember from the lesson before, to get rid of natural logs, remember natural log has a base of e. So to get n by itself, I'm actually going to exponentiate there a little bit. So what that does is it gives me e to the 2.56 equals n. Because remember, natural logs and e's as bases of exponential functions are inverses of each other. So to go ahead and figure out what's going on here, I basically just take e and raise it to the 2.56 power, and I get 12.935. All right, now what that indicates is roughly 12.935 days would be how long you could expect milk to last if you kept it at 34 degrees Fahrenheit. Okay, so again, story problems, I understand they're story problems, but again, you're just taking a look at what you're given, which we rewrote a little bit up there, to understand how it differs from the parent function, and then just understanding what the model represents. Okay, T of n represents, or T represents the number, or excuse me, represents the temperature that we're keeping it at. N represents the number of days that we can do that. All right. So again, hopefully, this got a little bit longer than I wanted it to, but hopefully a lot of this stuff is kind of review as far as how the different translations and transformations, as well as reflections, affect different functions. And it's really no different than what we've done, on multiple occasions throughout the year. So just make sure, again, if you have questions, make sure you ask. Otherwise, just make sure you're prepared when you come to class.